All right, so up until this point, I've been kind of going around the idea of giving away a proton for acids, accepting a proton for bases, but I haven't fully explained or defined what we're actually dealing with in terms of the equations. The Bronsted-Lowry definition of acids and bases introduces an additional concept that is actually very useful and one we're going to be utilizing a lot in this class, the idea of conjugate pairs. Conjugate pairs are substances that differ by having one less H plus or one more H plus than each other, right? So for instance, the following acids: hydrochloric acid, perbromic acid, chloric acid, sulfuric acid. The conjugate base of each one of these acids is literally going to be the same thing, except that you'll have one less H and the charge is going to go down by 1 unit. So instead of having HCl, the conjugate base will be Cl minus. Instead of having HBrO4, you'll have BO4 1 minus. And the same thing goes for the other substances. One less H and the charge goes down by 1 unit. Each of these pairs are referred to as conjugate pairs of each other. This is the conjugate acid, the one that has the most H's between the two, and the one that has the least H's is the conjugate base. But the difference between them can only be one single H plus. If the difference is more than H pluses, you're not dealing with conjugate pairs. Alright, so those are the conjugate bases. They're going to have one less H than the conjugate acid, and its charge is going to be one less than that of the conjugate acid. And we've already kind of looked at that specific feature when we introduced the balanced equation for the acid dissociation in water for the acidic substance. Now here, HA being the acid makes water behave as the base. And that's kind of important because the acid will generate its conjugate base. The base will generate its conjugate acid, right? So between HA and A minus, HA has more H's, so that's the conjugate acid. A minus has the least amount of H's, so that's the conjugate base. Between water and hydronium, hydronium has one more H, so that's the acid, and water has one less H, so that's the base. And the idea right here that I want to highlight is that on either side of the reaction, you're always going to have acid reacting with base or base reacting with acid. What you're not going to have is acid reacting with acid or base reacting with base. That's an important concept to keep in mind. Now for deriving the conjugate acids from the bases, all you have to take into account is that the acids will have more H's than the base. And if you're dealing with a conjugate acid, you can only have one more H than you do have in the bases. So if you start with OH minus, you're going to generate H2O. Notice that we have increased the amount of H's by 1 unit, but we've also increased the charge by 1 unit. The same thing is true for oxide. The conjugate acid, the direct conjugate acid of O2 minus is not water, it's actually hydroxide because it has one more H and only one more H than oxide. Same thing goes for sulfide. And ammonia, if you want to derive the conjugate acid, it will have to have one more H and its charge will have to go up by 1 unit. So you'll have NH4 plus, known as ammonium. And then phosphide, the direct conjugate acid will be HP2 minus. Now for some of these substances, you can actually go forward. In fact, you can actually start adding more H's and more H's until you get to a positive charge for the entire molecule. But the idea right here is that you can add one more H plus and you increase the charge by one more unit to derive the conjugate acid of the substance. Now, some of these substances, as I was saying, can actually continue taking up protons even further, right? So hydroxide can take up another proton to become water. Water can take up another proton to become hydronium. The same way that sulfide can become hydrogen sulfide and then turn into dihydrogen sulfide or hydrosulfuric acid, and then take up another proton to become the H3S plus derivative. Now, when you look at this entire range of reactions, what I want to convey very clearly is that the direct conjugate acid of oxide is hydroxide. The direct conjugate acid of hydroxide is water. the direct conjugate acid of water is hydronium. The one thing you have to be careful not to say is that the conjugate acid of oxide is hydronium. That's not true because they differ by 3 H's. The difference can only be 1 H if you're dealing with the conjugate pairs. Alright, but the other thing to be highlighted, especially for the substances in the green box, is that because they have H's, they can behave as acids. But because many of them have lone pairs present, they can also behave as bases. And so this act of either being a base or an acid is what we refer to as having an amphoteric substance. It can behave in either way. And the way you tell which way it's going to behave is based on the other reactant present or the other species on the reactant side. If the species is considered a strong acid, then this will have to behave as a base. Or if this other substance is considered a strong base, then this will have to behave as an acid. And that's how you tell the difference as to which way the reaction is going to go from the point of view of the amphoteric substance. It's all determined by the second reagent present in there. All right, now the conjugate base, if that's what you start with, and going back to the base dissociation equation, the base reacting with water automatically makes the water behave as an acid. It has to, because you can only react a base with an acid, the same way they can only react an acid with a base. Now between A minus and HA, which is the conjugate of A minus, the one that has the greater number of H's is the acid. The one that has the least amount is the base. And the same thing goes for water. You go from having H2O to having OH minus. So that means that water is now the acid and hydroxide is the base. And once again, you have that base plus acid denomination on either side of the equation. All right, so now we're going to use that information to, make some predictions, right? So here I'd like to show you a derivation because it's actually kind of cool, and at least it gives you a mathematical means of determining whether the reaction is going to be product favor or reactant favor. So I'm going to write the equilibrium expression for this hypothetical equation. We have an acidic substance reacting with a base. The H plus is given to the base, so you have A minus and HB plus as products. So you have the following equilibrium expression. If you play now with a mathematical trick, which is that I'm going to add hydroniums to both the top and bottom portion of the fraction. So technically what I have here now is no different than what I had before, right? I'm multiplying and dividing by the same thing. So I'm not changing the numerical value of this equilibrium constant. What I'm doing, however, is now introducing a new thing in here, because if you look carefully, you have A minus times hydronium over HA, and you have HB plus divided by B and divided by hydronium. Those are literally the Ka expression for the acid and the the opposite of the Ka expression, the second Ka expression for the acid. So technically speaking, what you actually have here for this equilibrium is the Ka of the first acid, the one on the reactant side, divided by the Ka of the second acid, the one that's present on the product side. So here's where the mathematical function comes in, because I'm going to take the natural log of, I'm going to take the regular negative log of both sides. So the negative log of the equilibrium constant is going to give you pK, but you're going to have negative log of Ka1 over Ka2, which can be split out into negative log of Ka1 minus the negative log of Ka2. So you end up with the following expression: pK equals pK1 minus pK2, where pK1 is in respect to the acid in the reactant side, and pK2 is in respect to the acid on the product side. Alright, so what do we do with this? Well, you look at the values. You actually look at the pK values and simply subtract them from each other. pK of the acid on the reactant side minus the pK of the acid on the product side. If the value is less than 0, what this will tell you is that this is actually product favor. This means that the reaction will definitely go to the product side. If the value is greater than 0, this will not go to a great extent to the product side. In fact, it will remain in the reactant side for the most part. And in some cases, you could even say that there is no reaction if the value is definitely very, very small compared to 1. So just by looking at that value, whether it's positive or negative, you can tell if this is going to go to the product side or not. All right, so with all of that being said, this finishes the first lecture that deals with acids and bases. It's not going to be the last one, and in fact, we have at least 3 more lectures that will dwell with the reactivity of acids and bases. So get used to this idea of defining your Ka equation, your Kb equation. Definitely remember your pH and your pOH. All right, so we'll stop the video right here.